Okay, welcome back everybody. We're going to start our light and optics unit today, and I don't want you guys to take notes when you're watching this video right away, but I'm going to post a second video kind of describing how I think you should be taking notes, and I'll kind of walk you through the notes that I would take for this lecture. Then moving on, you can use that same strategy to take notes with the lectures you see beyond this, because you'll notice you're going to be given all this stuff. Like you're going to have access to all this stuff. So you won't have to take notes the traditional way. But I still think that there's a way that you can take notes that will help you understand this stuff and retain this stuff a little bit better. So I'm going to teach you that in the second video. Let's get started. So energy can be released in a variety of ways, like heat, light, or sound. What we can conclude from this statement is that light is a form of energy. Okay? And specifically, light is electromagnetic radiation that is visible to us. So one of our first property of light, our first basic property of light, is that light is a form of energy. This means that the first law of, or all the laws of thermodynamics, I suppose, uh, apply to light, but the first one is the one we're going to pay attention to. So the first law of thermodynamics states energy cannot be created nor destroyed. It can only be changed from one form to another. This means that light is always the result of some other form of energy or reaction. So we're not really creating light, but we are changing something into light, okay, often through chemical reaction. Okay, the second basic property of light is that light travels in a straight line from its source. And the easiest way to kind of demonstrate that for yourself is put your hand up in front of your screen, cover something up, and the light doesn't bend around your hand and you see what's behind your hand anyways. Light has to travel in a straight line. It's a little more apparent when we look at something like lasers, because those do shoot in they're visible uh, lines of light, and they shoot directly straight. That's why laser levels are a really useful tool. And we'll get into more of this later. It won't kind of come into play until we talk about refractions and reflections and stuff like that. So let's talk about electromagnetic radiation, or EMR. EMR is a type of radiation that has both electric and magnetic fields. That's why it's named electromagnetic radiation. It includes gamma rays, X-rays, UV rays, or ultraviolet, visible light, infrared, microwaves, and radio waves. You've probably heard of most of these, maybe not gamma rays, but most of these other ones you've probably heard of. EMR is classified by its wavelength, so how long between peaks. And why don't we draw this? It'll be a little simpler to show. So we'll pull this up here, and let's say we have got 3 different wavelengths. Let's say this is our first one. I'll try and make these as even as possible, but I'm kind of bad at drawing. So here's our shorter one, and then here's our longer one. Okay, so the way you measure a wavelength is you go from one peak to the other peak. And let's say we measured that and it turned out to be 400 nanometers. And if we take a look at the peak of this one to the next peak, it's significantly longer. Okay, so let's say that one is like 1,000. And then this peak to this peak is not very far at all. Oops. Nanometers. Now that just looks like a bunch of M's. I'm sorry. Let's clean that up. So 100 nanometers is our shortest wavelength. So we say this is a shorter wavelength. And this one would be longer than our original 400 nanometer wavelength. So that's how you measure wavelength. Ones that have very, very long distances between peaks are considered to be long wavelength. Ones that have very, very short distances are considered to be short wavelength. Uh-oh. So the smaller the wavelength, or the shorter the wavelength, the higher the energy level of that electromagnetic radiation. Which means if we go back to our beautiful drawings, the shortest wavelength there has the highest energy level, where the longer one has the lowest energy level. And only a very specific wavelength of EMR is visible to humans, about 400 to 700 nanometers. So if we take a look at our diagram but blown up, you'll notice that the visible spectrum is very, very small. It's just this little sliver here. And visible light for violet is about 400 nanometers, maybe 390 or something. And it goes just over 700. Okay, and then you'll get red. So we know that violet light, purple light, has actually the highest energy level because the short wavelengths are down at this end. The long wavelengths are over here. So red actually has the longest wavelength of visible light, which also means it has the lowest amount of energy. And you'll notice down here we've got gamma rays, X-rays, and ultraviolet as kind of our really high energy short wavelength. And then you get kind of the longer wavelengths up here: infrared, microwaves, radar, radio. I think the easiest way to remember that short wavelength stuff has high energy is if you imagine something along the point, traveling along this point here. Let's say this is like a little particle or something right here. And if it's moving this way at the same rate as a particle right here moving this way, this thing is going to be going like this, super, super fast. And this thing is going to be kind of like chilling, going a little slower. So I like to think of the ones with shorter wavelengths as kind of like these little hyperactive things that bounce up and down really quickly, whereas the longer ones kind of move up and down pretty slowly. So that's how I remember it. I don't know, hopefully that'll work for you. So here's some uses of the different types of EMR. Oh, I got to pull it up on here, excuse me. So different types of EMR, we've got gamma rays. Very commonly we use those for like sterilization. So in hospitals or places that are kind of doing some medical stuff, they might take their needles, their syringes, and all the stuff that they're going to be using, and they might expose them to gamma rays, where they're basically just shining gamma rays at them. And that will actually end up killing all the microbes and bacteria on those implements. And then they can actually use those on people and they'll be clean, right? They won't have any of these kind of nasty things that could get into somebody's body. X-rays we use in medicine and dentistry. Probably this is where you've seen it used to see past the layers of skin and muscle, and it doesn't go through bone, so you get those kind of like skeleton outputs, those pictures of your skeleton and bones and stuff. You can see fractures and all this kind of interesting things. Ultraviolet we also use for sterilization, and I would assume you can use X-rays as well. The reason you can use these ones is they're higher energy, and if you expose something to enough radiation of a high energy level, it will cause mutations. And if you cause enough mutations, it'll just make that thing die, basically. It's also the reason that your dentist will probably go behind a like a lead pane or like go behind a wall or something when they're giving you an X-ray, because they don't want to be exposed to like 20 X-rays a day. You get exposed once in a while and it's fine. It's like not a big deal. But if you get exposed to a lot of it, it will start causing mutations. And the most common mutation from kind of radiation exposure is cancer. Um, so that's essentially what we're doing to microbes. We're giving them a bazillion X-rays or a bazillion gamma rays uh, at the same time, and it ends up killing them and sterilizing whatever we're trying to sterilize. And then ultraviolet's kind of cool too because you can detect forged banknotes with them. There's some properties of ultraviolet that we use for detecting forgeries, and you've probably seen it for glow bowling. Again, this won't like if you go glow bowling, you're not going to die from getting ultraviolet rays. But there is a way that we can use it to sterilize things. Sometimes you use them when you're camping or something. Visible light, obviously we use that for illumination, so we can see stuff. Microwaves, we use that for cooking. That's why microwave ovens are called that. They literally shoot microwaves out to heat stuff up. We also use microwaves for communication, and radio waves are mainly used for communication. So that's it for today, guys. We'll get into this tomorrow. And I want you guys to check out the second video I'm going to post. And I'm basically going to be going through the PowerPoint, through what I just taught, and I'm going to model how I would take notes on that stuff. Okay, cheers, guys.